very much for being here. I'm very looking forward to tell you a little bit about quantum computing and the work we do at Sussex in order to achieve that, and also in our company, Universal Quantum. So let me just try to share. I don't actually have a share button. Maybe you need to allow me to share, because I don't have the ability to share. Oh, here we go. Share my screen. Perfect. Good. Oh no, it's still disabled. Host disabled participant screen sharing. Still disabled. So I can't. So I think on your side, in your setting, you need to allow me to share my screen. Oh, fantastic. Now that works. Good. Outstanding. Can you see my screen? Good. Oh, it's outstanding. Right. So as I said, I'm gonna speak about quantum computing. I don't know how well questions will work, but very happy to answer questions even during my talk. We don't have to wait till the end. Obviously, now with this electronic format, everything might be a bit more challenging, but I love questions. So please don't hesitate to ask anytime, and certainly let's make plenty of time after the talk. But if you like to, I don't know how we do this electronically, if somebody in the room likes to ask a question, then we need to see how we maybe if somebody can just let me know, and then I'll very happily answer at any time. So as I said, so I'm going to talk about our efforts to build practical quantum computers, and maybe also tell you a little bit about what quantum computers really are, what they can do, what they can't do, and maybe why I'm so excited about doing this work all together. But okay, let me see. No, hopefully good. But let me start with the most important thing first, and let me introduce you to some of the real heroes who do this incredibly hard work I'm gonna talk about. I'm very lucky to have a really outstanding research group at the University of Sussex, who really work extremely hard in having realized some of the things you're gonna see today, and so this is really something which is very hard, and so these guys are amazing in making these tremendous achievements. Equally, I should acknowledge our funders. So as you can imagine, building quantum computers is immensely expensive, and I'm very lucky to have the trust of so many funders. And you can see on the bottom here that this is a very broad range, from the European quantum flagship to US, various US funders, to Innovate UK, to EPSRC, and the various other agencies, and so we're extremely thankful for that. So let me get started and show you the first conventional computer. So it's a transistor, and so that's how this whole thing started in conventional computing, and we all know where it went. Computers got faster and faster, something which is often illustrated by Moore's law, where computers increase their speed, or the number of transistors they can contain periodically, and I guess at some stage it becomes more difficult to make things smaller and smaller, and so that's kind of where you go to the scale of single atoms, where computers really can't increase speed in the same way anymore as maybe they have done in the past, and one could imagine this to be a challenge and a problem, but I guess a very famous and extremely smart physicist, Richard Feynman, actually took this as a opportunity and asked the question: when we go so small that we really dealing with individual atoms, can we use this as an opportunity to then make things happen according to quantum mechanics, this rather strange theory, which gives rise to rather surprising predictions. So what are these predictions? Yeah, predictions are that you can be at two different places at the same time, and an object can be at two different places at the same time. In my PhD, I was lucky enough to work on a prediction a theorist had made to make an atom move both forward and backward simultaneously. And indeed, we managed to actually do the experiment to show exactly that. And you may have heard of quantum tunneling, where an object can tunnel for a wall, for an energetic barrier, and maybe the most mysterious and most strangest quantum phenomenon is entanglement. Einstein called it spooky. He called it spooky because it's extremely counterintuitive and something which it's very hard to get our head around, and coming from this classical world. But the world isn't really so classical. And today, and maybe in this talk, I'm going to show you a little bit how very strange the world is when you go to a small scale, and when you look very small objects like atoms. And this has really driven my enthusiasm to be in this field for many years. So, but beyond a long period of investigation, where physicists try to get around these very strange phenomena, some physicists thought, can we actually tame these very strange phenomena to build some type of new technology? And maybe this was the birth of quantum computing or quantum technologies in general. And this is really very different. Quantum computing is very different to conventional computing. But maybe what it shares in common is the same trajectory of development. So this very long development that we've seen in conventional computers. So what is it? What can a quantum computer actually do? And it really can solve certain problems which would take even the fast supercomputer millions or billions of years. And if you're more mathematically minded, it changes the actual scaling of how long it takes to compute a certain problem. And so to be maybe more concise and more exact, I've given you a number of applications where quantum computers are known to have distinct advantages as compared to conventional computer. And so the famous algorithms, search, factoring, optimization, and machine learning. And so you've all probably used the internet to make payments. So the way this is secure is via what's called RSA encryption, and that relies on the difficulty of factorizing large number. Equally, Bitcoin are encoded via what's called elliptic curve encryption, and again is secured via this difficulty. Another example is understanding nitrogen fixation, so it's understanding chemical reactions. That is very important for the production of fertilizers, and we know that quantum computers have the capability of delivering us a better understanding of this process. 2% of the world's energy is being used for this, so it's really a problem which is very interesting. Equally, understanding protein folding may help us find a cure for dementia. So there's lots of applications, but and maybe if I wanted to tell you what drives me or drives my fascination here is the fact that obviously quantum mechanics is the theory which describes any other physical system. And very quickly, simulating or evolving quantum mechanical equations becomes intractable on a conventional computer. And so that means we have to use a lot of approximations, which then typically are not quite so accurate anymore. And so what quantum computers may allow us to do is to really simulate these quantum equations exactly. And so that's the idea of digital quantum simulation. So that could have impacts across many fields, whether it's material science, simulating new materials like maybe high temperature superconductors or chemical reactions or new pharmaceuticals. So this is why this is so really interesting. So people ask, how do we discover the most important quantum computer applications, and in order to answer that question, I always relate back to history, so to these famous citations of Thomas Watson, who in 1943 is said to have said that there's maybe a world market for 5 computers. And so I think this is not because Thomas Watson wasn't unbelievably competent in what he was doing, but simply because it's very hard to predict the future of such an emerging technology. And I want to show you this newspaper clipping here about the birth of computers. So I'm going to read that since it's written very small. So the electronics people said there were too many vacuum tubes and they would never run. The mathematics people said there were no problems complex enough that computers were needed. So, so I think all of this in some sense illustrate the naivety when we think of these new technologies, and hopefully that answers the question whether we are really completely settled with what quantum computers can do. So, so let's talk about how to build a quantum computer, and you make use of what we call the superposition, so quantum superposition. So in as I said before, an object can be in 2 different places. We call that quantum superposition. And now applied that to a computer. Now, rather than information is stored in bits, so a string of zeros and ones, and now a classical bit is either 0 or 1. Now, a quantum bit, in stark contrast, can be 0 and 1 at the same time, and that obviously gives rise to a very, very different functioning of a quantum computer. And so to illustrate this, I've got this little example with 2 bits. So the world's worst memory stick, where you then in a classical 2-bit memory, you can choose what you want to write in there. So for example, you might choose to write in 0, 1. But because a quantum bit can be both 0 and 1 at the same time, so then you don't have to make that choice. You can actually simultaneously write into 2 quantum bits. You can simultaneously write in 0, 0, 0, 1, 1, 0, and 1, 1. And so that kind of seems interesting, but kind of not really that great, because instead of writing in 1 number, so this 0, 1, I can just write 4 numbers. Interesting it becomes when you start increasing the number of quantum bits. So let's do the same comparison for 100 classical bits, I can just write in 1 long number. But in a quantum computer now, I can write 2 to the power of 100 different numbers in there. And so that you can see this is a very, very big number. And so this big number shows you in a maybe very simplistic way of how a quantum computer works, is how much more powerful a quantum computer can be. Now, I should say that this is a very simplistic explanation, and there is a lot more subtlety in how a quantum algorithm works, particularly in the sense that quantum measurement now would require us to only at the end of our calculation only to get one of the results. But the fact that we can encode these different superposition states means that in a way we can do work on certain problems that allow us to do encode all these numbers simultaneously to give us one answer that maybe depends on all of these different calculations. So to become a bit more specific on the development of machines, people have spent a lot of time working on developing algorithms, and maybe there's 2 computational regimes that strike out, and the one computational regime which is what is currently the state of the art of quantum computers is what's called noisy intermediate scale quantum devices. And what that means is that you don't correct for the inherent errors of every quantum operation inside your quantum computer. And because you don't correct for these errors very soon or very quickly, as you do more and more operations, the errors accumulate. And that means in turn that you can't really do anything useful beyond maybe 50 to 100 qubits. And this is kind of where the machines which you can access today from home, from IBM, for example, or Google, these have around 70 to 80 qubits. Now, there's a different regime, and this different regime is referred to as fault-tolerant quantum computing. And within fault-tolerant quantum computing, you can correct for the inherent errors of all your operations. That's good news that you can actually do that, and it wasn't so straightforward that in fact that's possible. So this is a really amazing theory which has being developed to enable that. But there is a price you have to pay, and this price you have to pay is that instead of just using the qubits you require for the for solving the problem, you also need a lot of extra qubits in order to correct for these errors. And so how many extra qubits do you need? Quite a lot. So quite a lot means that eventually you'd need a machine that can host millions or even billions of qubits. And so this is a very, very technical, hard problem, which means the hardware has to be really appropriate in order to ever get us there. So what kind of technology should you use to build a quantum computer? There's plenty of different platforms you can, because nearly any physical system behaves according to quantum physics, and it will, as such, in principle, you can use to build a quantum computer. Now, the kind of leading platforms right now are superconducting circuits. So this is a circuit made out of a special material which is superconducting. And this is the platform which is being used by IBM and Google. Now, another very promising platform are trapped charged atoms or ions. And one of the big advantages that this platform works at room temperature. And maybe let's just quickly have a look at why the difference between these platforms. I will talk today about trapped ion quantum computer and computing, and now I'm going to try to explain why is it that we use trapped ions and not superconducting qubits. A lot of people ask me, why aren't you using superconducting qubits if companies like Google and IBM do that? So the reason is, in a way, very simple. Superconducting qubits require cooling close to absolute zero temperature, so to minus 273 degrees Celsius. And that means that you have very, very little cooling power available. So the ability to cool a large mass of materials is a cooling power. Only very little cooling power is available at that temperature. Now, in stark contrast, trapped ions are room temperature technologies. You can actually trap ions at a chip, with a chip that sits at room temperature. And typically, we just use mild cooling, and that mild cooling isn't so much because of the quantum physics, but because of the actual silicon microchips we use. And the big advantage of working at these very mild liquid hydrogen temperatures, so this is around 70 Kelvin, is that you have plenty of cooling power available. And what means plenty? Means hundreds of watts. And this is a comparison to a milliwatts. We're talking 6 orders of magnitude more cooling power. And that means that you can then handle and use a lot more qubits, which means that you can really imagine scaling such a machine not just to 70 qubits, but maybe to thousands or millions of qubits. And that's, as I said before, is so important when you want to build quantum computers that can do really useful things. And so what I'm going to tell you today about is how we use trapped ions, and how we use trapped ions in conjunction with silicon microchips in order to build a practical quantum computer. But let me just introduce you the main actors here. Each bright dot is one single charged atom or an ion, and so this is a picture from our lab. We trap these ions inside a vacuum system, and again, I could now give you the appropriate physics literature or a beautiful physics book, but actually there's a different book I can show you, which strangely and surprisingly gives a rather accurate description of this. So Tom Clancy in his novel Mirror Image indeed gave a rather beautiful description of what is a trapped ion quantum computer, and so I thought I'll share that with you because it's so nicely and simply expressed. So he says, you can find ions in webs of magnetic and electric fields, hit a trapped particle with a burst of laser light to send it into an excited energy state. Then hit it again to ground it. That's your switch. Rows of ions in a quantum logical state. giving you the smallest, fastest computer on Earth, neat, clean, and perfect. And this is remarkably accurate, because besides the last sentence, which is a complete lie, if you come into our lab, you'll find that it's certainly not neat and clean, and quantum computers are far from that. They're very messy machines. So how do you encode a quantum bit into a single atom? And the way to do that is using first we have to think of what is an atom, and it's an atom in a very simple picture is constituted of a nucleus and an electron. And so you can think of the internal state of the atom as a different trajectory of the electron going around the nucleus, and you can change the state of this electron making use of laser beams or microwaves. And so you can go from one state to this red trajectory to the black trajectory, to the black state here via, for example, use of microwaves. So, but we need to first understand how we actually trap an ion. And so let's start with that. So what you'd need is some kind of minimum in the electric field. So this minimum would look something like that. But unfortunately, there's a very annoying physics law which actually forbids this entirely. And so physicists had to come up with some trickery how we can do that. So this is not allowed. And so instead, this is what physicists came up with, which is what we refer to as a quantum-motive potential. Now, if you would sit in one of my physics lectures, I would now go over to solve Matthew's equations and show you and prove to you using these equations that this is actually trapping. But since I'm an experimental physicist, we've also built a little device, which I'm going to show you now. So it's a saddle, and if I place this ball on the saddle, you can see that this ball just rolls off. But now when I start to rotate the saddle, you can now see that the ball indeed stays confined on this rolling saddle. So it's really proof that you can keep this ion trapped. And so how does this look in our laboratory? This is a vacuum system. Inside this vacuum system is extremely good vacuum, and we need that because we don't want any collisions with other atoms. And so then we pump out this vacuum system. We have this microchip inside, and just behind this window, which you can see here, this is where we have the microchip, and that's where we hold the ion on on this chip. So this is a nice picture where we open the window, and you can see this little black square. And so if I zoom into that little black square, you see a microchip, and so the ion is now levitating above this microchip. And in fact, this is kind of how that looks like. So you can see the surface. This is kind of a picture of one of these microchips, and all of these shapes are electrodes. So you can apply a different voltage to each of these electrodes, to each of these shapes. I'm going to use my laser pointer to show a few things. Here we go. So you can see the ion is now levitating a hair width above the surface of that chip, around 120 micrometers. And by now changing the voltages here, the ion can now move along these paths across. So this is kind of like a game of Pac-Man, really, where you move the ion across, transport it. In a way, the execution of a quantum algorithm is moving these ions, crossing this labyrinth, and in between executing a quantum gate, so logical interaction between one ion. Remember, each ion is one qubit, so between one qubit and another qubit. And so these gates, along with shuttling operations, this constitutes the execution of a quantum algorithm. So quantum gates are logical operations with one or two quantum bits. And so, for example, one 2-qubit gate, a logical operation would be that depending on the state of qubit 1, I'm going to flip the state of qubit 2. So that would be, for example, what we refer to as a C-NOT gate. And you can show that any quantum algorithm consists out of a set of these, what we call universal gates, if I have enough of these gates, that means I can execute any quantum algorithm on a quantum computer. Now, traditionally, this has been done by so implementing or executing such a quantum gate has been traditionally done using pairs of laser beams. And so a lot of the work in recent years has really been very impressive work in recent years has been done like that. But remember, all the quantum computers which are in operation right now, they have very small qubit numbers. And so it's not that difficult to align pairs of laser beams with sufficient accuracy in order to execute such gates. Now, but again, if you now start thinking about the engineering required to scale this up to millions of qubits, you probably wouldn't want to be sitting there and align millions of pairs of laser beams with an accuracy of 100th of a millimeter or even better in order to have this computer operating. So there's another way, and that is to execute quantum gates by applying voltages to a microchip. And this is very analogous to actually how our conventional computer chip work. This idea makes use of the use of microwave technology. This is something we invented in Sussex in 2016. So this is the idea of quantum computing with global fields. And if you're interested, have a look at this paper. And I'm not going to go in much detail here but I'm happy to do this also in question time if you're interested to explain this diagram. But essentially, you can think of this as some kind of radio transmitter where we place an ion in a particular location of a very strong magnetic field gradient. And what a magnetic field does, it actually changes the separation of these two energy states here. And ion can only absorb global microwave fields if this energy separation is exactly equal to the frequency of these global fields. And so by moving the ion then into a particular position within this magnetic field gradient, the ion essentially tunes into these global fields. And as such, by applying a particular voltage, now either executes here as in the green zone, a single qubit gate, or for example, if you have two ions and we apply a different voltage that will tune these two ions into these red microwave fields, and they will now undergo a 2 qubit gate. So the big highlights of what you see here is that, as you can see now, the number of fields does not scale with the number of qubits in your quantum computer. So independent of whether you have 2 qubits or 2 billion qubits, you need the same number of frequencies, same number of fields. And this obviously is extremely helpful when you imagine scaling something like that to really millions or billions of qubits. And so this was maybe the big opportunity and breakthrough, which made us really, really enthusiastic to go about now thinking about how to build large-scale quantum computers. So one microchip can hold only so many qubits. That's very simple. Think of a microchip be a finite size. These things are made in a microchip foundry, and the machines to produce these chips have only a certain size. So every microchip can not be bigger than a certain size. So that also means that you can only fit so many qubits on one microchip. If you want to go beyond this kind of size, you really need to have some kind of modular solution. So you need to have a modular quantum computer. And the idea of modular quantum computing has been developed for quite some years now. And in fact, pioneered in America in a group of Chris Monroe, making use of what we call photonic interconnect. So I'm going to show you this now. Here, there's a quantum computing module here. There's another quantum computing module here. and it turns out if you connect an optical fiber from one module and another optical fiber from another module via beam splitter to two detectors, you can entangle or do a quantum gate between an ion on one module with an ion on another module. And that's really good news, because that means now I can build some kind of network of quantum computers, and I could scale this to arbitrary sizes. Now, the world record in speed, and in fact, the world record for this technique has been achieved at Oxford University, and the world record is 180 per second with a fidelity of 94%. So that means that there's an error of 6%. The fidelity is 94%. And the problem with that is that this connection speed is very slow. And if you look closely at the experiments to achieve that, these are very, very complicated experiments, so huge experiments. So it's kind of hard to imagine how something like that would scale up to millions of qubits, or to thousands of such modules, and how we would connect them. So the University of Sussex, we tried to come up with an alternative solution. And in 2017, in this paper, we proposed the idea to make use of electric field links between adjacent quantum computing modules. So you can see here that you shape the shape of the electrodes in such a way that you can make electric field links. You can transport ions from one quantum computing module to another quantum computing module, just using electric fields. So this was a bold idea we've put in this paper in 2017, and we then subsequently went on trying to achieve that. But maybe the first important step here is to really think about why this is maybe a good idea, and the first reason is that it's very simple. The engineering to realize the idea is very simple. All you need to do is align two microchips with an accuracy of 10 micrometers. You see, there's no optics here. There's nothing particularly sophisticated, and you can actually make this very simple. But more importantly, the connection speed, or not more importantly, but equally important, the connection speed can be much, much faster because you use electric field links, and that is very important to build practical devices. So in 2017, we wrote about the idea, and again, in physics and maybe also in engineering, many people have many ideas, and while these ideas may sound great, you really have to show that that works. That it's not just some mad idea, and there's just something really stupid about this idea, which may not work. And so the first thing after publishing this paper is we started building up an experiment at Sussex, a prototype experiment to actually show that this really works. And so this is a picture here of the prototype from the outside. It's a vacuum system, and right here on the top, this is where we're going to have two rather sophisticated microchips. And so you can see a microchip here and a microchip here. And there's a little gap here. I'm going to zoom in now so you can see that there really is a very smooth gap here. And so I'm very happy to announce now to you a very, very exciting breakthrough. And from going from an idea, we have now managed to really show that this idea really works. And so we've achieved some really, really exciting results. And so we managed to transport ions at a rate of 2,400 per second. And again, like just to remind you, the state of the art result that had been realized at Oxford University was 180 per second. Now, equally, Oxford University, in order to make that their link, they generated a fidelity of 94%, so 6% error. And maybe this is the most impressive part of our demonstration. So we managed to realize this with a ion transport success fidelity of 99.999993%. So this is an extremely high number, and makes this immediately capable of building a essentially fault-tolerant quantum computer. So these specifications are good enough, both fast and good enough to really use this in practical devices. And this number is only limited for the engineers or people, enthusiasts who understand a little bit more electronics. This is only limited by a very embarrassing digital to analog converter we use here. So this has a speed of 130 kilosamples per second, and a very loud cutoff frequency of a filter. And so means this technology can easily scale up to even much, much faster rates, even though it's not required. So, so on weekends, when I don't do physics, I go running sometimes, and I run usually maybe 8 kilometers. And now what I'm going to show you now is that our ions can run longer. So if you look down here, you see an ion that is now being transported from one module to another module. So it will appear up here, will go back and forth. And in order to even measure the loss or the reliability of this process, we actually made this ion move for 10 kilometers, so a little bit longer than I run on weekends. I find this extremely impressive if you think about it, especially since this distance is only very, very small. So this ion went over and over, back and forth, and this is really got us into this really impressive number. So this is, I think, this is a brand new result that will be imminently published. And now I want to walk you a little bit through of how we're going to go really about building this larger scale quantum computer. And so, as I mentioned, in 2017 at Sussex, we led a collaboration which included Google, Eureka, and Aarhus University, and Siegen University, in putting together what we call a engineering blueprint of how you go about building a practical quantum computer that could really host millions of qubits and as such capable of solving really interesting problems beyond the capability of the fastest current supercomputers. And so we start in this blueprint with this idea of an X junction where the ions levitate above this microchip. And so you have a zone where you can detect the quantum state of the atoms that you need that to get the result of your computation. There's a zone where you then entangle one ion with another. So you do a logical quantum gate between two different ions. But then even with this fantastic vacuum, every so often you will lose an ion because of a collision. And so you have to have a loading zone, so the ability to reload ions. Remember, imagine if you have 1 million ions, it's going to be every so often a loss into a loading zone. So that's kind of the idea of that. And so this then is being made using a kind of microchip, as you can see here. So you see this microchip design. And now this is also a really exciting result. So recently we've been able to make such a really powerful microchips. You can see here an X junction, including current carrying wires that enable us to carry out this entanglement generation. And all of this gives rise to what you see here, a type of electronic quantum computing module, where here on the surface you have these ions trapped above the surface, above this array of X junctions. But below the surface, you have to have a lot of electronics. So this electronics is here to generate all these voltages. You need lots of digital to analog converters. But then you need also electronics to even calculate what kind of voltage actually needs to be applied where. So that's done by some kind of ASICs, electronics, field programmable gate arrays, FPGAs. And now there's a lot of density actually. So you need to think of the cooling. So you need a working cooling system to cool all this electronics. And that's actually the reason why we operate at 70 Kelvin, because silicon turns out is actually very highly heat conductive at 70 Kelvin. So that allows us to remove the heat very fast of all of this electronics. And just to show you that this is not such a mad, crazy idea, so I'll show you a comparison to a classical microprocessor chip, which also has this multi-layer architecture. The big difference here is that everything is here much smaller. So this is really fairly big because ions need to be held very far away from the surface. But in principle, in terms of the functionality, there's a lot of similarity. So this is a little film I want to show you to see how all of this comes together to make a quantum computer. So you load ions into your circuit, you transport an ion to the gate zone where you do, for example, here 2-qubit quantum gate, making use of these global fields and a magnetic field gradient, which is made using these current carrying wires below the surface. You then, if you wanted to measure quantum state of the ion after the calculation, you can read out the quantum state making use of these low global laser beams that go across the architecture and using integrated detectors. So this quantum computer really looks like a game of Pac-Man. So this is the execution of quantum algorithm. All in parallel, these ions move across, executing this quantum algorithm. And so this works on a single wafer, maybe a few hundred junctions. And if you want to be bigger, then obviously you need multiple of these quantum computing modules, these microchip modules. And now I'm going to show you again what we've already seen in the experiment. Now I'll show you the animation. So, so the ions can't shuttle across if these modules are not well aligned sufficiently. And if you now align these modules well enough, then you can connect the electric field lines and the ions can simply transport to the next module. Now, depending on the application you have in your mind for this quantum computer, you may need a different number of qubits. And by just adding more and more quantum computing modules, you can build yourself basically a large grid of quantum computing modules, enable you to then really eventually host as many qubits as you require to solve a particular problem. And so this is kind of the vision of how we go on about building these practical quantum computers. But how is this going to happen? So all this work started as a research group at the University of Sussex, and I've shown you the really heroes, the group picture, and many generations of PhD students and staff developing this technology, inventing this technology. But a research group can't really build practical technology. So in fact, you wouldn't have one physicist to build anything. You wouldn't want physicists to build a bridge or to do brain surgery. That's really, you want experts here. And so the same thing really applies to quantum computers. You need the right engineering to be done in order for that to happen. A research group can only really do prototyping and investigate the underlying principles. And so in 2018, we founded a company called Universal Quantum. And so the idea of Universal Quantum is to really do the heavy lifting engineering in order to build practical machines with these large qubit numbers. And so it's a full stack quantum computing company. So we work both on the software and the hardware in order to build such a machine. And the idea really is to develop these fully electronic quantum computing modules using foundry processes and to actually build practical quantum computers. And so this is obviously an extremely expensive goal to have, and so this wouldn't be possible without an amazing network of investors. So so these are our investors. So Village Global is investor who's supported by Jeff Bezos, Mark Zuckerberg from Silicon Valley. Hoxton is a very famous fund. You may know them actually if you ever order food. They have funded Deliveroo, 7%, giving rise to Oculus Rift, this virtual reality environment. And all our other investors are equally amazing and really helped us to source the right team in order to make this happen. So source the very best engineers and staff to really help all of this. So our headquarters is in Hayward's Heath, so just in the vicinity really, where we built laboratories, and we're very lucky. We have got this whole building at our use, and fantastic council who've been really working with us very closely to make this happen. So we are now building practical quantum computers. We are building the very first air-corrected quantum computer in the UK, which is funded by Innovate UK, and we do this together with Rolls-Royce. So we work on developing applications for aircraft engine design. We work with many subsystem manufacturers in the region, universities, and other partners. We've raised a little bit more than 7 million to make that happen. So that kind of brings me to the end of my lecture. So I hope I've tried to been able to give you a bit of the fascination of why I got in this field. I've been working on this now for 20 years, and it took my fancy. And when I started in 2005, many people rolled their eyes at me and said, "This is all impossible. It can't be done." I think it can, and we are now doing this. So the applications are highly disruptive in many sectors, but we really only just about starting to learn about some of these applications. And there's just like in conventional computers, we're going to see a lot of development of these applications. So there's many different approaches around the world in building quantum computers, and all of these are extremely valuable and should be pursued. What makes us maybe a little bit different is the ability of this approach to scale to really large qubit numbers, and we can do this, but because we make use of microwave technology, the same technology as what you've got in your mobile phones. So for me, quantum computing is really something which has always pushed my imagination, and maybe it does so with yours as well. And so I'm gonna like to end my lecture with actually asking a question to you, and think about what could an unbelievably fast computer operating unlike any other technology we now really do. So thank you very much.
Thank you for talking to us. I'm very reluctant to ask you to take questions, Winnie, because it sounds like you need to rest your voice.
Please don't worry. I love questions, and I would be deeply disappointed if I couldn't have questions. I'm fine. I've already tested negative 2 days ago. I'm absolutely fine.
Maybe get a glass of water. I know from experience, COVID is not a minor infection. Are there any questions in the chat? No.
You don't use cavity QED to enhance the ion field interaction.
Yes, this is a very good question. So I'll just repeat the question for everybody. So do we use cavity QED to enhance this interaction? So cavity QED is actually an extremely challenging technology. So actually at the University of Sussex, we have a world-leading expert to implement cavity QED with trapped ions, Matthias Keller, and he's really developing this. And if you ever get the chance to look in his labs, you'll see a huge and rather complicated experiment. Cavity QED with trapped ions is unbelievably complicated, and so the reason why we're not using it is because it's so complicated and so difficult that it would be difficult to scale this up to large qubit numbers. So nobody in the world has yet managed to do this on a chip, and these chip experiments are unbelievably complicated. So this is in a way you could do. If I go back to this slide we saw before, oops, sorry, this was here. This idea of using photonic interconnects. You could actually use cavity QED in order to facilitate this process. And this is a very active area of research. Matthias Keller is really a leader here in this. He's doing amazing work. But this is only in the beginnings, and I don't expect that to be capable of being implemented in a quantum computer for another 10 years. And so we don't want to wait another 10 years. We want to build quantum computers right now. That's why we made this alternative electric field link technology that is, as I showed, really available right now, and we've now demonstrated this with tremendous speed.
Can I take a question from the room?
I was wondering, when you have these qubits, can you, if you have like a set of qubits, can you encode? Is the super state that like with states where it's a 1 and a 0 at the same time? Is that only in the single qubit, or if you have like a set of them and you store two numbers and have it be only those two numbers?
You need me to. Do you need me to repeat that?
Yes, please. That would be helpful. Yep.
When you have a qubit, see if I've got this right. They can be in multiple states. But if you have multiple qubits, can you use that to store more numbers than for a single, than the multiple states of a single qubit? Have I got your question right?
Yeah, so like two specific numbers.
So two specific numbers.
So I mean, maybe I'm not 100% sure whether I understood the question, but let's have a look at this, for example. So if I have a single qubit, so all what I can do is, rather than being 0 or 1, it can be 0 and 1. So but if I have now two qubits, I already can encode 4 numbers. So the more qubits I have, the more different combinations I can encode. So so with two qubits, I can encode 4 numbers, and obviously with 100 qubits, I can encode this rather large number of different numbers simultaneously. Maybe to add to my answer, because I fully understood your question. There are also Q-trits and Q-dits. So instead of having a qubit where it can be 0 and 1, it can be, for example, 0 and 1 and 2. That would be Q-trit. And people are working on new hardware, actually using trapped ions. For example, people have built Q-trits and Q-dits. And the advantage of that is then that you need less ions, less particles in order to encode a larger number. But the disadvantage of that is that you then also have a lot more complication in interacting with each one of them. And so that kind of, there is not such a clear advantage to go to more than 2 states in the ion in order to then do that. But there is a paper by a research group in Austria who was actually shown that they can actually build a quantum computer using, or I shouldn't say a quantum computer, but they can do all the kind of rudimentary operations in a Q-trit or a Q-dit. Did I answer your question?
I guess my question is, when you have the 2 qubits and you have those 4 states, is it possible to encode it being only 3 of those states and not the whole 4? Or does it have to be the whole 4?
Oh no, absolutely. No, yeah, absolutely. Yeah, sorry, yeah, that's yeah, absolutely. You can completely write into there whatever you'd like. So you could, for example, only in a qubit, you could only write in 0, 0 and not have these. So that's absolutely right. You can choose what you code completely.
Thank you.
I hope you can see that Thomas R. Clark said your talk was coherent as a laser.
No, I haven't seen it. Oh, thank you very much. That's amazing. Thank you so much.
Any more questions?
Yeah. Is there research at the University of Sussex or with Universal Quantum just doing computing or like algorithmic applications, or is it mostly hardware based?
The question was, is either the University of Sussex Quantum Group or Universal Quantum doing software research, or is it purely hardware based?
Both entities do software and hardware research. So one of the things we've done recently, we've calculated as part of the research group, we've calculated then the hardware specifications required to break Bitcoin encryption, and so that was a very interesting topic, which got us to work very closely with Interpol. So that was really interesting. interesting output. We also studied of how many qubits and what kind of hardware specification it required to simulate a particular molecule, a FMOCO molecule, which is really important for nitrogen fixation. So we carry out this kind of resource study and software study in the correction of errors in the research group. We have a really fantastic faculty member at Sussex, Neil de Boudrop, with whom we collaborate, who thinks a lot about correction of errors and quantum algorithms. Equally, in the company, we developed a full stack. So the full stack means we start very much at the bottom where we control each qubit, but we develop full emulators for quantum computers, and we develop applications. So we work with Rolls-Royce, for example, on fluid dynamics. So fluid dynamics is obviously very important when you design and develop aircraft engines. So you can't really separate the two, hardware and software. They really go hand in hand, because when you learn how to what kind of software requirements you have, you can then much better develop the software, and there's a really, very strong interplay between the two. Also, particularly in correcting these errors. So this is something we are very, very active about. We developing, as part of a UK-wide consortium, a quantum computing operating system. This is the UK quantum computing operating system. So we're very active in this, and this is. I should really stress that the development of the software and the development application is equally in its beginnings as the development of hardware, because don't think of a quantum computer as kind of just running software. Don't think of a quantum computer as a fast computer that runs normal software, but any problem and application you want to solve with a quantum computer, you would then require particular software or the particular quantum algorithm in order to solve that problem. And so this development really needs to go hand in hand, and we're very enthusiastic about doing this. And in fact, Sussex is very keen to further expand this engagement in software development in informatics department, and this is extremely exciting research field. So if you study informatics right now, this is certainly something you should consider becoming active about. This is really an amazing, really mind-boggling new way of doing programming.
I'd like to, I don't know if you can see the chat, but I'd like to ask a question that Stuart Newborough has asked in the chat, because I think it will be in the back of a lot of people's minds. The way he's written the question is, could we get in a position whereby encryption becomes pointless because another quantum computer would just crack the code? Do you want to tackle that one, or?
Yes, absolutely. So as I said, there's a particular quantum algorithm available which can break RSA encryption, and also the elliptic curve encryption, which is being used for Bitcoin. And so when you make a credit card transaction on the internet right now, you are making use of RSA encryption. When you use Bitcoin, you make use of this encryption right now. But obviously, it's now well known that we will have quantum computers that eventually can break this encryption. And because of that, institutions like NIST in America, and also GCHQ, the National Center for Cybersecurity, they're working very intensely to develop alternative encryption. And these encryption protocols are made in such a way that it's very unlikely that one can find an algorithm for a quantum computer that could break this encryption. So these are very, very clever computer scientists who kind of have a good feeling of how a quantum computer works, and so they're devising now algorithms that are hopefully resilient to quantum algorithms. So in Bitcoin, that means, for example, there will be a branching off, where essentially, like, once we get closer to these quantum computers, we will have a branch off, and that means also that will become quantum resilient. Now, so that means we are still a little far off until quantum computers can break RSA encryption. By the time we will have quantum computers powerful enough, we will also have encryption protocols that will be then reasonably safe. What may not be safe is information which is transmitted right now using these older encryption protocols, and a party could now proceed and save these transmissions, knowing that they can't break them right now, but once a quantum computer is available, they could break them then. So this is something one should be aware of, that existing encryption is not resilient, but there will be future encryption, which should be very, very safe.
Thanks for that. Have we got any more questions? Cool. You might need to shout, or I'll repeat it.
That's okay. I wanted to pick you up on the asterisk note on your final slide, where you gave a slight hint that you might be sympathetic to the average interpretation of quantum mechanics. I've got a memory that David Deutsch at some point said that the existence of a quantum computer would actually prove the many worlds hypothesis. What's your take on that? And does it really make any difference, the interpretation that you place on what's actually going on?
So I've just the other day I read an article, I think in CNN, telling me that actually the many worlds interpretation has given rise to so many movies in film, and something which is important to point out. It has certainly infused me into studying physics and being blown away by quantum physics personally. So I think what this does is it shows you really how strange nature is. It shows you how counterintuitive is what we see here. Now, as a physicist, I'm a physicist, not a philosopher. I read sometimes philosophical books, but that's about it. I'm definitely a physicist, and as a physicist, I'm not allowed to take a side in an interpretation, because I have no experiment available to distinguish between two different interpretations, and I'm not aware of any kind of way how I can distinguish via any kind of empirical experiment which interpretation is correct. So what I'm left with here is my imagination and how I started in physics. I wanted to be science officer in the Enterprise. That was in primary school, and just so thinking about parallel universes and this is an unbelievable fascination. And maybe what you say, I think, is really important. How David Deutsch really started investigating quantum computers was wanting to have a means to distinguish between what interpretation would be the right one. And while maybe we don't have yet a means to distinguish between these interpretations, what that does tell you is that when scientists, when physicists do blue sky research and think about very fundamental things, very trying to understand the very fabric of nature, what they might just do accidentally is to develop some extremely disruptive technology. And so I personally have fascination with the many worlds interpretation. I have not dug deep enough to really give you anything with good confidence to say you should go with one or the other interpretation. But I find that this really always empowers my imagination and reminds me every day on what an amazing topic I'm actually working on.
That's a really amazing answer, actually. And I'm inclined to say I am a philosopher, and given a choice, I would take the many worlds interpretation because it does so many good jobs outside physics as well as physics. But I appreciate that a physicist is not going to take that position because it's something that should be determined by experiment. There was another question.
Yeah, I have a sort of more practical question. What do you think is sort of the timeline to progress from prototype to something that is used, like that is available in more broad application?
Did you hear that question?
No, if you could repeat that would help.
What do you think is the timeline from prototype to practical computing? That's basically your question, right? Yeah, can you give us some indication of what you think? I mean, admittedly, it's speculation, but what you think the timeline will be in the development of this as a practical technology?
When I started in 2005, my group at the University of Sussex, I named it Iron Quantum Technology Group, and many of my colleagues rolled their eyes, and nobody talked about quantum technologies or quantum computing, and this has now really seen a very, very strong change, and I would refer to what we see now around the world as quite a hype. So companies overtake themselves with more and more hypiest claims and saying, hey, are we going to be faster, bigger, better? And I think this is a very dangerous thing. Building quantum computers is very, very difficult, very hard. And by trying to kind of overtake yourself with promises of when you're going to have this machine, it's not helpful. I try to do this the other way. So I've been giving my lectures, for example, about this idea of building these electric field links. I never agreed to tell anybody when will you have done it, and then one day, and that one day was actually only recently, I actually managed to show you the slides and show we haven't just done it, we have done it better than we thought, and so I much prefer this way. But I mean, I realize I haven't given you a very satisfactory answer. So to give you a bit of a feeling and to maybe go against some of this hype, I should say that maybe we are still looking at maybe at least 5 years until we have the very first possibly interesting application. And we certainly look at time scale of 10 years to have these really powerful practical quantum computers. So this is simply because you have to now integrate a lot of these individual achievements we have made into a single machine, and that will just take some time. But what I can say, and what I'm very confident about, much more confident than ever, is that we can and we will have disruptive and practical quantum computers. This is now not just something scientists dream about. It is something we can certainly do, and hopefully what I've shown you today in my lecture, that we have really ticked off and realized many of the key milestones on the path of this. We've got technology solutions that work, and so now we make them happen. So it's still a very long, tough journey, and for any, unfortunately, I can't see the audience, I can't see who sits there, but if you're interested, if you're studying, if you're just getting into science, if you're in high school, then it could have never been a more exciting time to do this, because for the first time we are now really just building machines that can do useful things. We're not just exploring the strangeness of quantum physics. So it's an unbelievably exciting time, but it will take some time, and it will be a slow process. Will in not so long time actually have useful practical quantum computers.
There's 3 questions in the chat. Do you want to take them, or do you need to rest your voice?
No, my voice is fine. I've still got a lovely glass of water.
Okay. Shakir says, how do you see quantum computing impacting AI and ML? That's the first one. If you just want to say something, you did say in your lecture that it is going to be very significant in that.
Yes, it certainly impacts. I'm not an expert in machine learning applications. There are quantum algorithms that will help with that. I think it's way too early to say on the level of disruption, and I'm simply not a deep enough expert to give you a really expert guidance on this. So I rather like to keep my answer short by saying that I certainly expect a very distinct impact, but there's a lot of literature I could refer you to where people write about this, and maybe that would be the best way look at that. I don't want to be the person who says, "Oh, wow, quantum will change everything," or equally, I don't want to say it's not important. But this is a really, really emerging and really fascinating field. Something I would definitely recommend becoming more active in.
And there's one from left field here, from David Newey, who says, by removing the error factor of the qubit, are you removing the capacity for a quantum computer to be created?
So the error factor, let me just have a look at, I have now the error factor of the qubit. So think of the error of the qubit. Actually, classical computers also have errors, and the nice thing about a classical computer is it's very easy to correct them because you do 3 operations rather than 1, and you take the majority vote, and we are very lucky, or we're very likely to correct for this error. So the errors in a quantum computer, in a classical computer, stop it from working. We must correct them. Same thing in a quantum computer. So the what means creative? Well, that's a very loaded question, and I should probably refer this to you as a philosopher. But certainly the ability to execute a quantum algorithm depends on the ability to limit or reduce the errors, and so that's really important. So unless you can reduce these errors very quickly, the errors would accumulate and then accumulate to then give rise to a result that doesn't mean anything anymore. So to be very short, then now I think quite the opposite. By mitigating the errors in the quantum computer, we actually enable quantum computers to work across many different applications, and one of them obviously is machine learning, and so that's where maybe creativity is you could argue is something what comes in here.
And from Remy Cornwall, he says, so what would be the first killer app? I actually think we've discussed that already, but you might want to make another question.
Absolutely. I mean, this is really important, and I mean, everybody has their own favorite first killer app. For me personally, the biggest motivation is that you can understand other physical systems. And what does that mean? It means, for example, understand chemical reactions. That means maybe create new pharmaceuticals. And this is something really important. This one example, I think, which I find really exciting, is nitrogen fixation. We are living in an age where energy is more important than it's ever been before, where the future of our planet may depend on us reducing our energy consumption. Nitrogen fixation makes use of 2% of the whole energy being used right now. If you can reduce this a little bit, and please don't trust this, we need to do plenty of things before we have quantum computers to reduce our energy consumption. Quantum computers are not the magic bullet right now, because they're not going to be ready for quite some time. We need to do many other things right now to reduce our energy consumption. But for me, that would be a killer app to help with this. Creating pharmaceuticals, chemical reactions is for me what's really interesting.
We missed one from Mr. Clark. Would you consider exploring a hybrid system of shutting combined with photonic interconnects between monolithic clusters of many ion traps? I'm not sure I fully understand that question, but that's what he wrote.
So I can kind of and I think what he means is, and it's a very good question actually, is shuttling. So not shutting, shuttling. It's just a spelling mistake, I suspect, and photonic interconnects. and absolutely I would. So the problem with photonic interconnects that they maybe take another 10 years to be developed, and we want to build a quantum computer right now. So, but absolutely, and once photonic interconnects are at a sufficiently high technology readiness level, then one may well imagine networks of quantum computers, even far distant networks of quantum computers, where we have one quantum computer here and it can connect it via some fiber network to a machine elsewhere, to a machine in London or in Oxford. So all these things are possibility. And yes, absolutely, I can imagine this. It's just that I want to build this machine right now, and photonic interconnects are nowhere close to being ready for this purpose. But in the far distant future, absolutely, this may be a very interesting thing to think about.
Yes, thank you. I really do think you need to rest your voice and recover from what is quite a serious infection. And can we thank Professor Hensinger? Thank you very much for doing this. Seriously, thank you.
Really fun. I really enjoyed this, and thank you also for the wonderful and lovely and very fantastic questions. So I really enjoyed that too.